I would like to go through the proof of the division algorithm, not by looking at the proof in the book, but by pretending we're trying to prove this from scratch ourselves from the start. And I'm essentially going to just show the scratch work and not the finished product. I want to illustrate the thought process of how somebody might think of proving the division algorithm if they've never seen the proof before, they don't have a book available. It's too long and difficult a proof to put on the exam completely for you to do from scratch. However, I could imagine maybe I've done this before, putting the proof on the exam where I write a lot of it, but I leave some blanks in spots for you to give reasons. So it's still worth for you to understand what's going on. But again, what I really want to do is talk about the problem-solving process. So division algorithm, it's kind of a funny name because it's not really an algorithm. You know, the word algorithm means essentially procedure, a procedure that stops to do a task. But the division algorithm is really a theorem. But the name has stuck for a couple thousand years. The division algorithm was known by the ancient Greeks over 2,000 years ago. What does it say? Given two integers, a and b, with, just to keep it simple, b assumed to be positive, a could be negative. The conclusion is, then there exists unique integers, q and r, q standing for quotient and r standing for remainder, such that two conditions hold. A equals BQ plus R, and R is between 0 and B, possibly equal to 0, but not equal to B. Both of those conditions are part of the conclusion. And again, the backwards E exclamation point means there exists. Okay, this is the division algorithm as a theorem, which you learned with numbers when you did division back in what, 4th or 5th grade. You know, back in 4th or 5th grade, you first started learning about doing things like what is 22 divided by 6. And you figured out the answer was, well, the quotient is 3 and the remainder is 4. Why? Because 22 equals 6 times 3 plus 4. And notice the remainder, 4, does satisfy the property that it's greater than or equal to 0. 0 is less than or equal to 4. And it's less than the b. What's the b? The b is 6. The b is the thing you're dividing by. You're essentially trying to describe a divided by b in this division algorithm without using division symbols. Just dealing with addition and multiplication. How do you go about proving this? So what we're going to do is not the final finished product, but the scratch work for the proof. How could you imagine trying to prove this from scratch if you've never seen the proof, don't have access to it, that kind of thing? Try and do it on your own. It's pretty hard to imagine. It's like, well, I can see examples. These examples seem pretty clear, but examples are not proof. Don't be afraid when you're working on homework to have some scratch paper out. Do some doodling. Try some ideas out. That's what you got to do in scratch work. And one thing you might try here is write down the conclusion that you're trying to show. A equals BQ plus R. And well, sometimes it's handy to rearrange the equation a bit. For example, you could subtract BQ from both sides. Now, in this particular case, in doing that, it doesn't seem to help much. It's like, well, what good is that? The key thing that makes this a good idea to think about is something called the well-ordering principle. I'll put over here, the well-ordering principle. What does the well-ordering principle say? If you look in the book, it says every non-empty set of positive integers has a smallest element. Give me any set, non-empty set of positive integers. There's going to be a smallest positive integer in it. Right? Seems pretty intuitive. Does this take proof? You remember what the book says? What does the author say about the well-ordering principle? Probably don't remember. We're taking this as an axiom. Does anybody know what that means? Yeah, something we assume to be true. We don't try to prove it. It's a pretty intuitive thing, seems very reasonable. Give me a non-empty set of positive integers, no negative integers in it. Starting with 1 possibly. If the set contains 1, for example, 1 would be the smallest element. Maybe it doesn't contain 1. Maybe it starts with 17 and then goes from there. Then 17 would be the smallest positive integer. Could be a billion, could be a Google as the smallest positive integer in the set. It could contain all really, really big numbers if that's possible. But thinking about a number line and imagining drawing this set on the number line, there's got to be some smallest positive integer. By the way, such a principle does not hold if you talk about real numbers. Like even take the real numbers in the interval between 0 and 1 in the open interval. There's no smallest real number in that set. 0 is not in the set. Is it 0.00001? No, I can think of a smaller positive integer, real number. So the well-ordering principle does hold for positive integers, but it doesn't hold for real numbers. But yeah, we're not going to try to prove this. We're going to take it as an axiom. We're going to assume it's true. So how is that helpful? Think also about what you're trying to show. Part of what you're trying to show is not only the existence of Q and R to make these equations true, but also that R satisfies this condition. It can't be negative. It's also going to be less than B. It can't be negative. It can't be negative. Now, it could be 0, or it could be some positive integer. Oh, so maybe what we should do is we'd like to apply this well-ordering principle, perhaps. Maybe we should consider the set of all possible things you can make like this. And that's what's done. Let S equal the set of all integers of the form A minus B times. I'm not going to write a Q because I'm trying to save the letter Q for something specific in the conclusion of the theorem. B times K, satisfying the property that K is an integer and A minus B times K is greater than or equal to 0. Now, technically speaking, that set could include the number 0, and technically 0 is not a positive integer. So I can't quite apply the well-ordering principle to this yet. Now, you might argue, well, couldn't I just modify the well-ordering principle a little bit to say every non-empty set of non-negative integers has the smallest element? And yeah, you could. But that's not what our author chooses to do. Our author chooses to phrase this in terms of positive integers, and 0 is not a positive number. It's not negative either. It's in its own category. So based on this definition, it's certainly a subset of Z. That's the notation for subset. And it certainly contains possibly positive integers, but also possibly contains 0. We need to consider 2 cases. What if 0 is an S versus what if 0 is not an S? Well, case 1, 0 being an S is actually the easy case. If 0 is an S, that means there's some integer k, where a minus bk is 0, call that an integer q. 0 being an s means there's some k where that thing is 0. Call that integer q. That means there exists a q in Z such that a minus bq equals 0, implying that a equals bq plus 0. And there we have it. Q is the quotient, 0 is the remainder. I'll just make a side comment, i.e., B divides A. You don't need to make that side comment, but this does fit the bill of the division algorithm. We've got a Q and we've got a remainder 0. Although, what about the uniqueness? Let's think about the uniqueness later. We're just trying to prove existence at the moment. And when 0 is an S, yes, a Q and an R exist. And R does satisfy this condition, because I am assuming B is positive. All right, what about case 2? 0 is not an element of S. Then S must be a set of positive integers that's got to have a smallest element. Maybe we need to use the well ordering principle, and that's true, but there still is a question. Is it non-empty? Now that might seem like a ridiculous question. Is it possible this could be non-empty? It doesn't seem like it could be non-empty, because K can be anything. But you could ask, well, is it possible A minus BK is never greater than or equal to 0? Never strictly greater than 0 if I'm assuming 0 is not in there. Is that possible? Like what if A were negative? Could that mess things up? Maybe this is never a positive number. And the answer is no. You can choose K to make it a positive number, but that technically takes proof. How? The book splits it into 2 cases here as well. I guess I'm kind of doing the book's proof, but I'm trying to think a bit more in terms of scratch work, in terms of the thinking process. Subcase 1, we need to show S is non-empty. Subcase 1, A is positive. Will this set contain any positive numbers? Will it be non-empty? I guess if A is positive, you can just take K to be 0. I don't think that's the way the author does it, but it seems like you could do that. That means A minus B times 0 is A is positive. That's going to be an element in S because it's of the right form. That's going to be enough to imply S is not empty. Subcase 2, perhaps the trickier case. What if A is negative? Then we've got a negative number minus B times an arbitrary integer. Is there a way to show that's sometimes positive? It should seem intuitive since you have such freedom in choosing K. But I mean, if A is negative and you're subtracting B, which is a positive number, times K, it would seem like typically you're going to get a negative number here. Oh, but maybe if K itself is a big enough negative number, that would make this product B times K a really big negative number, and subtracting a really big negative number would result in a positive number. How big should K be, negatively speaking? Well, that could take some scratch work as well. Here's what the book does. It chooses K equal to 2A. A is negative in the subcase. 2A is more negative, so to speak, further away from 0. Maybe if we do A minus B times 2A, maybe this will be a positive number. You could factor out the A. That's negative in the subcase. What about that? I'm hoping this whole thing is positive. B is assumed to be a positive integer. Remember that? That was part of the statement of the division algorithm. If b is a positive integer, 1, 2, 3, 4, 5, 6, etc., yes, 1 minus 2b is going to be a negative number. Negative times negative is positive. If you're being extra picky about things, you might wonder, do we need to prove that negative times negative is positive? No, you don't. That is something that, technically speaking, if you were developing the full theory of integers, that you would have to prove that a negative times a negative is positive based on the definition of what a multiplication is. But we're assuming we know how to do addition and multiplication, basic properties. You could say we're taking basic properties of integers with regard to addition and multiplication as an axiom as well. Basic properties, you know. And yes, 1 minus 2b, if b is a positive integer, will be a negative number. Now apply the well-ordering principle. WOP here means well-ordering principle. S contains a smallest element. Which is going to be a positive integer. Oh, let's suggestively call it R. And I'm going to put a Z plus here to emphasize it's a positive integer. That's standard notation. i.e., there exists an integer Q such that A minus BQ equals R is the smallest element of S. A minus BQ equaling R does imply that A equals BQ plus R. So it's satisfying the equation of the division algorithm. What's left to do? We still have to prove uniqueness, which for the sake of time, I'm going to skip. Let's try to finish the existence, though. We're not quite finished with the existence, because what have we not done yet? We proved the existence of Q and R that satisfies this equation. We haven't proven uniqueness yet. We know the R is greater than or equal to 0 by case 1 and case 2. We haven't proved it's less than B. The big hint that hopefully this is going to work is the fact that we chose R to be the smallest element of S. That's going to be the key thing. Hopefully that will mean it's also less than B. It's relatively small, hopefully less than B. It's not clear how you're going to prove that. In such a situation where it's not clear, it often helps to try a proof by contradiction. Assume to the contrary that R is not less than B, R is greater than or equal to B. Maybe you want to say before this point, we want to show R is less than B. Try an argument by contradiction. What is an argument by contradiction? It's to assume the opposite of what you're trying to show and show that that assumption leads to something that can't be true. Therefore, your assumption to the contrary must be wrong. So the thing you want to show must be true. Say that again. We're trying to do a proof by contradiction here of this thing we want to show. Assume its opposite is true. Assume to the contrary that this is not true, which means this is true. Try to get some statement from that assumption that doesn't make any sense. That can't possibly be true. Like 2 equals 3. That can't possibly be true. That's not the contradiction here. If you get a contradiction, that means the original assumption to the contrary must be wrong, and therefore the thing you want to show must be true. Very important proof technique. But there's always the question of, okay, how do I use this assumption? It's probably got to be a contradiction to the fact that R is the smallest element of S. Smallest positive integer in S. That's probably got to be the contradiction. I mean, that's how we constructed R in the first place. What the book does is considers A minus B times Q plus 1. Now, again, we're sort of doing scratch work, imagining that we're trying to do this from the start. Why consider A minus B Q plus times Q plus 1? Well, for one thing, we know A minus B times Q equals R. For another thing, we know A minus B times Q plus 1 in parentheses would fit this pattern of A minus B K. Maybe, just maybe, it also satisfies that condition because of our assumption to the contrary. And if it does, that would be an element of S smaller than R, contradicting that R is the smallest. That's sort of you're hoping is what's going to happen. It's not clear that it will happen, but it's just something you try when you do the scratch work. So what do I do with this? Well, just do the only thing you can do. Go ahead and try to simplify it. Doesn't seem so helpful until you realize, you stare at this for a couple hours, you realize, oh, wait a minute. A minus BQ, that's R. This is R minus B. Okay, how's that helpful? I've never used my assumption to the contrary yet. Maybe I should use that now. I'm assuming R is greater than or equal to B, therefore R minus B is greater than or equal to 0. Therefore, A minus B times in parentheses Q plus 1 is an element of S smaller than R equals A minus B times Q. Why is it smaller? Because B is positive and Q plus 1 is bigger than Q. I'm subtracting really something bigger from A than I am here. Say it again. I got A minus something that is bigger than A minus BQ, which equals R. I'm subtracting something bigger here, so the result must be smaller. It is important that B is positive. That's a contradiction. When mathematicians arrive at contradictions, they often put what look like stars to the right of the contradiction, but it's actually two arrows pointing at each other. That looks like a star. And you'll often see them draw it more like a star, like that or something. But this is actually two arrows pointing at each other. That's the mathematician's symbol for contradiction. Contradiction. Therefore, our original assumption must be wrong. Therefore, R must be less than B. And yes, after this point, you'd also want to prove uniqueness, but for the sake of time, we're going to skip that.